This chapter is about acids and bases, and this section is about Bronsted-Lowry acids and bases. A Bronsted-Lowry acid is a proton donor. If a species or molecule loses a proton in a reaction, it's the acid. A Bronsted-Lowry base is a proton acceptor. If it accepts a proton in the reaction, it's a base. A Bronsted-Lowry base must have a free lone pair of electrons in order to bond to the proton. And we need to use the correct names when we're talking about the hydrogens here. A hydrogen without its electron is a proton. So we've been talking about proton reactions up above. These are proton transfer reactions, but we have to call them a proton. They're not a hydrogen. A hydrogen atom is a hydrogen with its electron. This is a neutral species, not an H plus species. This is a hydrogen. Also, a hydrogen is H2, the molecular hydrogen. A hydrogen atom with 2 electrons is a hydride. This is going to be negatively charged. So keep these in mind. Proton, H+, hydrogen, H dot or H2, hydride, H2 electrons with a negative charge. So let me remind you, Bronsted-Lowry acid-base reaction is one in which one molecule or species donates a proton to another one. And here's an example, and HA is a general form of an acid. H2O is given as the base for this kind of reaction. We're going to use H2O for a bit here in the next several examples. This is an equilibrium with the conjugate base, which is A- and H3O+. So the HA is the acid, the water is the base, the conjugate base is A-, and the conjugate acid is H3O+. Also, I want to point out that we're going to be using arrows like these blue ones I just put up there to indicate bond making and bond breaking. When you're making a bond, you're going to use a pair of electrons either from a lone pair or from some kind of bond, like a pi bond, for example, and that pair of electrons is going to grab the proton. At the same time, we're going to break the bond between the H and the A, and that pair of electrons is going to stay on the A, so we use an arrow to indicate that the pair of electrons is staying on the A, so it becomes A- in the product. So let's get back to acids and bases. The acid strength is a measure of the ability of an acid to donate a proton. So the stronger the acid is, the more it's favored to the right. The acid donates the proton and it's favored to the right. That means the KEQ is going to be larger because KEQ is the product of the concentrations of the products divided by the product of the concentration of the reactants. We'll get to that a little bit later, but KEQ gets larger as the acid gets stronger. If it's a very weak acid, then we don't have much of the A- and the H3O+. We have mainly just HA. It does not react with water. So water we're going to be using as a measure as a way to measure and compare the strengths of acid. That is, water functioning as a base. The more completely an acid donates a proton, the stronger the acid is. So a stronger acid is more favored to the right. I want to point out that some acids that we're going to call strong acids are not favored to the right. They're favored to the left, but they have a significant amount of proton donation from the acid to the base. And so some acids are actually favored to the left, and we're going to call them strong acids. A weaker acid will be less favored to the right. So a weak acid, we have very little proton donation from the acid to the base, that is to water in these particular cases. And so we have mainly HA and almost no A- for a weak acid. And the KEQ then is a measure of the strength of the acid. The larger the KEQ, the stronger the acid. Let me make some comments about the acid-base reaction up above. You will recall from general chemistry that in an equilibrium reaction we're going in both directions, and we have stable amounts of the acid, the base, the conjugate base, and the conjugate acid by definition. The reverse of the reaction is also an acid-base reaction. So if we're looking at it from the reverse, the H3O+ is the acid, and it's trying to donate a proton to the conjugate base, the A-, in order to get the components on the right side, that is HA and H2O. So we need to think about it from both sides. If we do this, we can think about this as a competition. The HA is trying to give up its proton to go to A-, and the H3O+ is trying to give up a proton to go to water. And the stronger acid will win out. So if HA is a stronger acid than H3O+, we're going to have mostly A-. HA will have donated its proton because it's a stronger acid. And let me remind you also about the bond making and breaking, because the arrows that we use for those, because we're going to see that all throughout the course of the semester, and it's going to be hugely important. The arrow starts at the electrons that are going to be making the bond, and if we break a bond, the arrow starts at the pair of electrons. In this particular case, the line segment between H and A, it starts at the pair of electrons and goes to the atom that it stays with. And we don't need to do that for the reverse reaction. By convention, we really only do that on the left side of the expression. So let me give you a couple of examples. This is formic acid on the left side, and the base is water again. And so in this particular case, water grabs the proton that's going to be connected to an oxygen and not the proton that's connected to the carbon. We're going to talk about why there's a preference for one proton to be lost rather than another. Essentially, it's going to be the most acidic proton is the one that gets lost. And so we're going to estimate acidities based on equilibria considerations like I've mentioned before. So water grabs the proton, we become the HCO2 minus, that's the conjugate base, and H3O plus. We have a KEQ, which I've mentioned before is the product of the concentrations of the products divided by the product of the concentrations of the reactants. And the KEQ in this case is going to be about 10 to the minus 2. So in this particular case, and in all of them, actually, as we're going to compare the acid strengths of different acids in water, where water acts like the base to grab the proton, we're going to use a very small amount of the acid when we do these kind of tests. And the reason for this is that bulk water has a very large concentration, about 55 moles per liter. If we use a tiny amount of acid, then even if the acid gave up all its proton to H2O, and it becomes H3O plus. If there's a tiny amount of acid, there's only a tiny amount of H3O plus, and so the concentration of H2O hasn't changed. And we're going to need to make that kind of estimation a little bit later on. So in this case, we have formic acid. It gives up its most acidic proton to water. And we're going to talk later about why the proton that's attached to the oxygen is the one that's given up. H3O plus also gives up a proton on the right side. It tries to give up a proton to go to the left side. In this particular case, H3O plus is winning out because KEQ is 10 to the minus 2. So actually, the components on the left side are going to be favored. Water, H3O plus, is giving up its proton, and that part is winning out. The KEQ of this reaction, 10 to the minus 2, slightly favored to the left. This indicates that H3O plus is a stronger acid than formic acid. Note, formic acid is not a strong acid, but we do call it formic acid. It is a strong enough acid that it's an acid in many circumstances, particularly in biological reactions. So we call this an acid. Just because it's an acid does not mean that the equilibrium is favored to the right. It can be favored to the left. But in that case, there's a significant amount of proton donation if it's an acid. Here's another example. We have an ammonium giving up a proton to water. I'm showing the arrows once again. We have a KEQ. We've got the conjugate base and the conjugate acid, and the KEQ, as I've shown before. In this particular case, the KEQ is approximately 10 to the minus 11. The acid could have come from a salt like this. The compound would be called methylammonium chloride, and we're not showing the chloride because it's a spectator in this particular case, and so we're only showing the acid component of that reaction. So this reaction is less favored to the right. That is, the KEQ tells us that it's much more favored to the left. So it's less favored to the right. So we say that the acid is less acidic than the one above. Then the KEQ is going to give us, again, a quantitative measure of how strong the acid is. And in this case, again, like in all the other ones that we do with H2O, as we're looking at strengths of acid, the acid is going to be in very small concentrations, so we don't modify the concentrations of water by a significant amount. Here's another one. This is an amine reaction with water. I've shown you the arrows, the KEQ. This time, wow, the KEQ is 10 to the minus 38. There's essentially no conjugate base and conjugate acid in this reaction. The amine on the left side, that is the acid in red, is an amine compound. That doesn't give up a proton to water almost no product at all. That's a vanishingly small amount of donation of a proton. And so the amine is a very weak acid, almost no deprotonation in H2O. It's about 10 to the 27th times less acidic than the example I gave you in the page before, where we started out with a nitrogen that had a plus charge because it had an extra proton on it. And we're going to need a much stronger base in order to pull a proton off of that kind of acid. So water is not a strong enough base to pull the proton off in any appreciable amount. And so one final example is a carbocation. A carbocation is a compound that has a carbon that has a plus charge on it, such as the one I'm showing you. Water is the base again. It's pulling off a proton and making this compound with a double bond, which is called an alkene. That alkene is fairly stable. This particular reaction, I'm not showing you the KEQ. I just want to point out that we could do this from compounds that have a plus charge and they become neutral, including compounds with a plus charge on carbon. So in this particular case, the acid is the carbocation that has a proton next door. We make an alkene product, which is has a carbon-carbon double bond.